Okay, so once again, I'd like to welcome you to our webinar on Unit 2, Air, Designing Scientific Investigation from Chemistry in the Community, the 6th edition. This is a part of our ACS ChemCom webinar series for the fall of 2012, and it is going to be recorded. My name is Michael Murray, and I am the Program Manager for ACS Textbooks. I'm here in Washington, D.C. this evening. I also have two wonderful ChemCom teachers that have been working with us for several years. Bonnie Bloom, who is at Hilliard-Davidson High School in Ohio, and Linda Tilton, who is at Woodlands Academy of the Sacred Heart in Illinois. Bonnie and Linda will be walking you through all of Unit 2 this evening. They'll give you some tidbits. They'll give you advice as teachers that have been through this. We're both piloters for this edition, and so Bonnie uses a hybrid version. Linda uses the 6th edition in her classroom. They both run workshops on the 6th edition, so we're really excited to have them with us tonight, and I know they will give us a great presentation and give us some wonderful advice. So as we move on, we're going to look at Unit 2. So again, in this unit, in previous editions of ChemCom, in the 5th edition, it was Unit 4, but it's been air, and during this unit, the students are going to learn a lot about air quality. They're going to learn about gas laws. They're going to learn all of these different properties and chemistry behind air. And the overarching theme of the unit is designing a scientific investigation. So students are going to learn these qualities about air, and then they're going to use that to design their own scientific investigation. So in Section A, they're going to look at properties of gases. B, they're going to look at the behavior of gases, look at kinetic molecular theory. In Section C, they're going to do how does matter interact and how does the energy work in the atmosphere. And in Section D, they're going to look at the air quality pieces. So as the unit opens, there's several pieces of headlines from different articles that are talking about air quality. And so as the students read this, they're going to ask themselves questions. What did these articles trigger in your concern? How does this affect you locally? How does it affect us globally? And what are some claims? So they're going to see all of these different claims. And throughout this unit, they're actually going to work through and to come up with their own claim, and they're going to design their own investigation. They're not going to complete the investigation, but they're actually going to do an investigation. So they're actually going to come up with the investigation, not doing it, so that they learn the process of inquiry and the process of being a scientist. So I am going to turn this over now to Linda. Linda's going to go through Section A with you. So welcome, Linda. Thank you for joining us tonight.
Well, hello, Michael, and hello, everyone out there. I'm hailing from northern Illinois, about 9 miles from the Wisconsin border, and I'm delighted to be here. Before we start, I just want to take a minute to remind you that in the ChemCom Teachers Edition, there is a lot of information before the unit actually starts for teachers. Planning lists of chemicals, planning guides, just lots and lots of things that will help you when you're actually planning when you begin to teach this. So let's begin with Section A. As in the beginning of all of the ChemCom units, every section has a list of goals. And in my classroom, we read these together as we begin, reminding the kids what we are going to be learning. And then they can come back at the end of the section and review them and see what they actually did learn. These have been a real hit with my students. I think the students today are real goal-oriented, and this just feeds into that for them. Let's see. We're going to begin then with a concept check. If you're new to ChemCom, this is also new in the 6th edition. There are questions that are going to hit information the kids have already covered and then offer them a question that they probably don't have a real good answer for. They may have some ideas. In my classroom, I use this as a talking point. We read these together, and then students offer different ideas. I make them jot down in their notebooks answers to the questions. They'll come back later and fill these in and improve on their answers. As all the new ChemCom units open with a big, broad experiment, properties of gases is the investigating matter for the air unit. This will take a little bit of time to set up, and in your classroom you'll arrange it so that it flows. The students are going to be given a series of experiments. I think there are 9 in all, and they will rotate through the experiment, each experiment having made a hypothesis or a prediction of what will happen in each experiment. And in my classroom, that's homework. And then they will actually, with their partner, go around the classroom and test all of the different experiments. These work really well. To us, they may seem like time-tested, but the kids really respond quite well to these. You will also refer back to these opening experiments as you go through the section and the entire unit, because this is a foundation. This will give them foundation for how gases act and what the students should and could expect. One tip I could offer for this opening investigation is have a bunch of balloons out so that the kids can change balloons when they're blowing into the 2-liter bottle or the bottle in Investigation 4. I also put out some paper towels so that the bottle can be wiped off, because some of the kids don't they have issues about putting their mouth on something after the rest of the kids have. I get big buckets from the paint store, and that's what I use for the water, to fill the water up for the experiments with the test tube and the glasses. Just looking through those, they all work really well. The last one, the Investigation 9, if you're going to have all of your students do that, if you're not going to demonstrate that one, you're going to want to have a bunch of cans, so that because every time the can is used, the students will, it's wrecked. Once again, you really should practice all of these before you have your students do them. And label well your lab stations. Moving along, A2 is going to give them introductions or reintroductions to these the big issue of pressure. I think that the textbook pictures really work well in reinforcing how pressure works. In our school, we have Physics First, so the students have been introduced to this before, but the units are quite new, so they do have to relearn those. Base units and derived units, again, this will be important for the rest of the year, and always a good idea to reinforce those. Following this, then, we have another concept check. This works really well. It's a really good picture of how force is exerted. This is, again, I asked students to do this one for homework, and then in their small groups they discuss it, and it really does the job. Applications of pressure, following that up, there are some really nice questions in this developing skills, which gives the kids an opportunity to practice what they have learned about, and these are quite conceptual. I think that also the sample problem on page, and I'm going to tell you the page if you're following along, page 159, the sample problems work really well, and my students, I find that they do go to those and use them as guides when they are doing their homework. But again, this is a really sweet way to handle pressure and force, which really is going to be followed up as we move forward and cover atmospheric pressure, which is the next section. Again, this is just giving the students some information about how pressure works with a great picture of the tornado. And since we have had so much unusual weather across the country, I think it is in a lot of their minds. The diagrams in the book are quite supportive. So also we get into some of the units of pressure here, which again a lot of the students may have had in earlier years, but we will be using the units now as we study gases. A5, pressure, volume, behavior of gases. We're over to page 161. Again, these diagrams in the book do tell the story, and we'll be getting into Boyle's law. And I think what's important about this is that the students now are seeing pictures. They've done a little experiment in section A1 with the syringe and air pressure, and I think the hands-on activity at the beginning of the unit really melds well with this particular Boyle's law, and for some reason I think the kids really get it. We follow up with reading the table, reading the graph, and then going forward using the formula P1 V1 equals P2 V2. And we will be then doing a developing skill using the information that we just gained. And again, I assign these for homework, and then we go over them together in class. I find my students do again relate back to those sample problems, and they do have very good results working through the developing skills, and also they really seem to grasp this concept. In the next section, A7, we're going to get back to what the whole unit is really about, and that is designing scientific investigations. And in this section, we're going to discuss and return to the idea of what is a good scientific question. We touched on that in the introductory unit. We talked about what makes a good scientific question. This is something that our students today are being asked to do a lot more than, say, in previous years. Developing scientific questions, designing experiments, investigating their own questions that rise from curiosity. So this is a really strong and important section of this section A. Evidence, experimental design, dependent variables are all going to come into play here. So once again, we're going to use vocabulary to try to get these ideas, have the students be able to get their ideas into play. Following this, we're going to have developing skills, A8. designing an experiment to investigate temperature, volume relationships, and they will be asked to write scientific questions, testable questions that will frame the investigation in investigating matter, which will follow A9. I have my students do these in their lab teams, and some years, depending on the size of the class and the students' ability to work together, I may have more than one teamwork on writing these. The kids will at first have a hard time with this, but you may have to guide them to get them to get into the actual activities. A9 is a wonderful Charles Law activity, investigating matter, exploring temperature volume relationships. Again, the students will be gathering evidence using hot oil, and I do this with the oil at my table in the front of the room, so I control the oil. The students come up by their lab groups. They come up with their capillary tubes. There are different ways to set this up. People have had really good luck using braces, rubber bands for the capillary tube and the thermometer. And I get the kids to bring in their braces, rubber bands for this, but I know that my colleague has used just rubber tubing that she cuts into thin strips. Bit of advice is to have the students lay these things down on a piece of paper when they pull them out to do their measuring. They will need guidance, and then to calculate their lengths. And also, Kelvin temperature is going to pop up here again. It has previously in the first unit, and in Unit 0, Kelvin temperature came up. So again, we're not teaching about Kelvin temperature. We're not teaching about it. We're using it. The students you will need to teach this. You will need to practice this before you do it, and you will need to teach this section, going over it step by step. And again, I think engaging the students and having them be part of the actual experiment really does help them to grasp this. And when you're all finished, again, you're going to go back to what was your question. Was it a good testable question? And what does this tell us about Charles' Law? This works pretty well. I get real good results with this. The students do. Gas laws don't seem to be such a hideous topic. The kids actually get it all. A10, then we're going to move on to temperature, volume, behavior of gases, and once again, these colorful pictures and this terrific graph help the kids to put this Charles Law into their memory banks. It's reinforcing, and it does help them. And it's followed up by developing skills, and the kids are quite successful at this. Again, I make this homework, and we talk through these, and then they work on them. We do a couple of practice problems during class that I have made up, and then they do the developing skills, which I quick check, and this is a homework grade that I give them. Followed up by concept check. Again, students now have ideas of what temperature and volume relationships are, and pressure and volume, and they will have mental pictures of these. And we will move on then to relationships, and question 3, how the relationships described in your answers to question 1 and 2 differ. So it's asking the students to concentrate and think at a higher level, and it's not just rote memory of vocabulary words, but they're actually asked to think about how these things are different. In A12, temperature, pressure, behavior of gases, again, they're given a formula, mathematical expression for the relationship, and followed up by developing skills. In making decisions, we come to the end of section A, and we follow up with, again, making decisions. As a first year teacher, this is something you might be tempted to skip because it looks like it's not learning gas laws, it's not practicing gas laws, but this is really important because it puts the thinking and the gathering information and the pictures of the gas laws into the kids' brains. I have them talk through these in their groups, and I have the groups set so that they stay in the same group for the whole unit, and they will then have put together, starting with, if you do it this way, they'll start with section A, and they'll have making decision questions, which ask them to write a scientific question that frames an investigation that they're going to promote and try to devise for their whole unit question. And it asks them to think about the variables that they're going to be using. Questions that it's just getting them started in laying down a foundation for the PIAT. This is definitely not something to skip. So I think the kids get a lot of this, and I have them keep it all together in one place so that they have, by the time they get to the PIAT, they have a good idea of where they've been and where they're going. I'd like to point out, as I move to the very end of section A before Bonnie takes over here, the section summary questions are really terrific. There is, and I'm on page 177, reviewing the concepts, and if you'll notice in the student and teacher editions, in a box in red letters, or bright orange letters or red letters, there is a concept that has been hit in section A, and then it's followed by some pretty darn good questions that the students now can answer pretty ably. And so I highly encourage you to have them look at these, and there are different ways to do it. There are lots of questions here. You could do it section by section and assign, one group of questions early as you're covering the material, and then as you move through section A, when you have talked about topics, then assign the questions that go with the topics. And also on page 179, what information can investigations provide about gas behavior? Again, this is a brightly colored box that's going to ask students to consider what they have been learning. Bonnie, I'm going to let you take over.
Okay. So now we are talking about section B. Am I doing it right?
Yes, I didn't turn the page.
Okay. All right. So section B, the goals are looking at the physical behaviors of gases. So it's kinetic molecular theory, ideal gas law, and the big thing in here is what is a theory, what is a law, what is a model, and how are those useful in explaining and predicting behavior. So let's take a look at some of those. In concept check 4, This question 1 used to be part of the post-lab questions with the air experiments that Linda talked about at the beginning. So now it's a concept check. Why can you drink with a straw? Why do you have to vent a tea kettle? Hopefully they can relate that to something they've seen. And then now we're starting to get to the molecular theory. What happens to the molecules in the sample of the gas? So it's talking about theories and models and how those are explanations. So there's observations and there's models. And then we start talking about the postulates of the kinetic molecular theory. Oh, I need to go back one. Michael, how do I go back? One more. Thank you. All right, so this picture is a really rich picture with a lot of information in it. So we can look at the idea of models as the particle model, and we can look at the helium inside as a particle and the nitrogen and the oxygen outside. And my students can get that this is the nitrogen because there's more nitrogen in the atmosphere, and this is the oxygen because there's less oxygen in the atmosphere, and that these are probably helium because they're single atoms, and these are diatomic. They can see the idea of pressure as the molecules bounce against the container, and they can see the idea of the motion as the molecules are in constant motion. So from a pretty simple explanation, you can have, or illustration, you can have a lot of explanation. And then they talk about the kinetic molecular theory and put it in terms of a modeling matter. So now students have learned about the kinetic molecular theory postulates, and they have to use analogies and models to try to treat bouncy balls as the particles and as they move around in a box. So again, we're focusing on, can you make it an analogy? We're reviewing the kinetic molecular theory, and we are taking a look at models. And students are pretty good at this. The next section looks at models, theories, and laws, and this is really where students struggle. The difference between a scientific theory and, as we're going on, we'll take a look at a law. So it starts with a theory that explains what happens. And they're explanations that can be used to predict results, models that are representations, and then we're going to go on and talk about what a law is. And students really have a hard time with the difference between a theory and a law. They seem to think that a theory can become a law, that a theory is not proven and a law is. There's a ton of misconceptions around the differences between theories and laws. And this section B really tries to hit that pretty hard. So we start with the ideal gas law, PV equals nRT, or as my students like to call it, PIVNERT. And from there, we can take a look at using the ideal gas law and units to try to do some calculations with them. And so this is the first time a lot of them have seen it's the same value, but it's different numbers depending on units. And so they can struggle, which one do I use when? Hopefully by this time you've stressed units enough that they know that they need to use units in their calculations. And so you need to make sure that your pressure units go with your R value. And that's really key for them. The other thing that it didn't occur to me where they struggle, pounds per square inch, PSI, or it could be abbreviated LB/IN squared. And they didn't recognize that those were the same. we tend to do most of our work with millimeters mercury, torr, and atmospheres. But they'll get familiar with all of these as they work through the problems. And so again, there's sample problems and developing skills, and they're solving for an unknown. I make my students actually make a chart, P, V, N, R, and T. 4 of those are known, 1 is an unknown, and then they have to rearrange the equation to solve for the unknown. I've also found that some students who struggle in math are better off putting the numbers in. I'm more comfortable. I learned to rearrange the variables and then plug in the numbers, but some of my students actually would rather put in the numbers and rearrange them rather than solve for the variable first. So again, like Linda does, these developing skills are usually homework. I'll have done some practice problems in class and some sample problems, and we'll have tried a couple together, and then this is their chance to do it independently. And they're pretty successful with this. Most of my critiques to my students tend to be show your work, use units, and things like that. And then we have concept checks. So we're talking about a scientific law versus a scientific theory. We're reviewing pressure and temperature, pressure and volume, and then this last one, transforming into a liquid, is the bridge to take us to the non-ideal gas behavior and then into phases of matter. So it talks about non-ideal gas behavior in a very qualitative way. My AP students will actually do some calculations, but at this level in a first-year chemistry class, under what conditions are gases non-ideal? And so we can talk about the idea that a law is very, very useful, but if there are circumstances where it doesn't work, we can modify that law. And if the assumptions aren't valid, then we need to make some modifications as well. And then that leads us into the next one, which is kind of in the middle of gases. We started talking about phase changes. So the gas is kind of the bridge to get us to looking at gases, liquids, and solids. And there's a lab that the first time I did it, well, it's the next slide, but we're going to look at liquid, solid, gas triangle. And for most of my students, this should be review. They're pretty good at the gas to liquid, liquid to solid. Gas to solid for a lot of my students is new. They get to look at a picture of mercury thermometers since we're not allowed to use them anymore. And then this lab is a pretty simple lab where they are just looking at crushed ice and heating it and measuring the temperature change over time. I actually use a Lab Pro or a graphing calculator and an Easy Link, so I use the Vernier stuff, that actually will collect the data and do the graph for them. It doesn't take very long, and at first I thought, well, this is kind of a simple lab. This doesn't show very much. But it really helps students understand that the idea that there's still energy going in even though there's no temperature change when we are changing phases. And it turns out that this will also be useful later on when we look at distillation. So it's a little bit of foreshadowing later. And now we're coming back to the air quality investigation. So now we're coming back to the questions they started to ask in Section A, and they're looking at their ideas of theories and laws, and they're looking at what they know about models, and now they're going to start to revise their questions that they want to ask, and what their investigation should look like, their theoretical investigation. And that pretty much wraps up Section B. It's not as intense as Section A. It's a little shorter, but it really talks about kinetic molecular theory, ideal gas law, Avogadro's law, and the ideas that theories and models explain, scientific laws describe. And again, that's where my students struggle, because in common language, what my students are saying, well, that's just a theory, they mean that's just a hypothesis. So it takes some time to get them to really understand that a scientific theory is not the same as our common use as a theory. And for that one, I try to ask it 3 or 4 or 5 different ways over the course of this section, just to re-emphasize, so I can hit that over and over and over again. And again, we'll take a look at the idea that not all gases are ideal. We'll look at average kinetic energy. This looks at the difference between heat and temperature and phase changes. And then the big summary question is, how are models and theories useful in explaining and predicting behaviors of gases? So like Linda said, these summary questions are really well written, and sometimes I'll assign them as we hit each topic. Sometimes I'll assign them as a review towards the end. But there's a really nice, for students who are doing writing, this section at the end is a really nice way to help students do some more writing in class. And then there's a little chemistry at work so that they can look at what's going on with chemists doing some chemistry, and then that brings us back to Section C. Linda?
Hello again, 'tis I. Section C is it's one of my favorites. Again, we're going to begin with the goals, and I hit these. In this section, we're going to talk more about the atmosphere and what the atmosphere is, what affects the atmosphere, what effects do changing your altitude in the atmosphere have, and what effects do radiation and different kinds of radiation have on the atmosphere. So the kids are going to get an idea right away about that, and they're also going to do some stoichiometry in this section, which are quite successful. My students are quite successful at this. We'll get into collision theory and catalysts, and then again back to gathering scientific evidence and how we use evidence to make claims about the natural world. The first concept check, again, these are good ways to tie things together in conversation during class discussion. I have the kids write the answers to these during class. We have writing time, and I say, you have 3 minutes you have to write, or 5 minutes you have to write, or 2 minutes, and I make them write. As Bonnie claimed, the English department is thrilled that we have the students write to communicate. And then sometimes I have them share their responses just within a lab group or 2 lab groups, and sometimes we share out with the whole class. But it's an opportunity to remind the students what we've learned and also to give them a glimpse of where we're going. This activity was in earlier sections, earlier editions. And there's a chem quandary in here also, traveling the atmosphere, that we use to set the stage for the C2. which is a developing skills graphing activity. I don't know about your school, but our students come to us and they all know how to graph and they're excellent graphers, but when you give them some data, they have a hard time with it. I have found in this book that as the year goes on, they get much and much better at their graphing skills, and to the point that I don't allow them to prepare graphs on computers. They have to graph them, and they get to the point where they really can manipulate, read, understand what a graph is telling them and what it's not telling them. In this particular activity, C2, there are two graphs that the students will prepare. One is plot air temperature versus altitude, and the other is pressure versus altitude. Of interest, my students will come back to me and say, could we use Kelvin temperature scale? They pick up very quickly that there are negative numbers in the air temperature, and Kelvin makes it a lot easier. And those that ask, I give permission. You'll have to make your own decision about that. The graphs are going to look the same regardless. There are some really down-to-earth questions, and I find the students are engaged with this particular graphing activity. Questions about the atmosphere and what it's like as you move up and down. Quite a good activity. This is homework. Depending on where we are in the school year and whether we have college night or play night or whatever, I sometimes will have each person make one graph. Sometimes everybody makes two graphs, but that's your call. The graphs then, at the very end, the kids are asked to draw lines through the graphs, and they find they have a picture of the various layers of the atmosphere. And they have, most of my students have an inkling that the atmosphere does have different layers, which moves us on to the atmosphere discussion, which now we have data, and we're going to plug it into what scientists tell us about these various layers, the troposphere, the stratosphere, and so on, and we will take a look at the gaseous components of the atmosphere, and again we come back to the reality of what the troposphere, the stratosphere, mesosphere, and thermosphere look like. And introduced here we have the idea of concentrations, and what does that concept mean. They have all heard of the various components of the atmosphere and the ozone hole, so there's a lot of interest at this point. Moving on, we are going to hit one of my favorites, and this is the modeling matter mixtures of gases. We're going to revisit what homogeneous and heterogeneous means. The students, I think, are amazingly in tune at this point with what that submicroscopic level of matter looks like. They are able to describe through pictures what a mixture is, what layers within a density tube, for example, what they would look like. If you'll think back to that picture of the Scientific American picture Bonnie talked about with the balloon, it's all tied in here. This is a perfect example of a spiral curriculum. They have been introduced to it, and now they're going to be asked to make some diagrams of what these things look like. I think this goes a long way in preparing them to write and balance equations. They have some conceptual ideas of what it is we're talking about, not just something that's totally abstract. I assigned the students to read this for homework, and then we work through it in class in stages. We do some of the questions together, and then I turn it over to them in small groups, and they work on them, and we report out. I have tremendous success with this. They'll be asked to think about what is a limitation of an activity, like drawing these molecules on a flat piece of paper, and that again is going to set the stage for talking about limiting reactants and limiting reactants in a chemical equation much later on. Terrific activity, and I have to say, I just have to put a commercial in for this, because I thought when I first saw these that the kids would hate them, and I find that my kids really like these. They feel that it allows them to explain what they understand. So give it the time that it deserves. And we follow up with a concept check. Again, we're asking the kids to tell us what they learn already and asking them to think about a question that they haven't really been exposed to yet. Collision theory comes up in C5. Great. I really think that it's a terrific diagram to explain energy. We talk through this some years, depending on the level of class, because some years I get kids that are really, really on top of things, and other years I get kids that are kind of slow. Sometimes we read this section out loud together. Sometimes I assign it for homework, but there's some great diagrams in the book to talk through what activation energy is, where is the energy when a reaction begins, where is it when it ends up. These energy diagrams are wonderful. And I'm sure for some of the boys in the classes, catalytic converter and how they work as far as energy goes is something that's probably right up their alley. And so there are some really nice pictures to accentuate that. And again, these energy diagrams I do spend a little bit of time on. I think that for what's going to come later, the kids do get a concept in their brain about how energy flows through a chemical reaction, and later on we'll get into this in more detail, but this is just sort of an introduction. In C6, reactions of gases, again we're going to talk about how these various volumes of gases work, and it's sort of the beginning of stoichiometry, and the way the book explains it, and if you follow the book and use it as your guide, the students get this. There's very little struggle if you talk through and work through all of these introductory reactions in section C6. We have talked about diatomic elements. We have talked about coefficients. We have talked about matter being not able to be created or destroyed. In our school, even though we're a Catholic school, we don't do miracles, so we can't create or destroy matter. The kids get it, and they're ready when section C7 comes along. The questions are well laid out. There's some very good sample problems. Again, we work through these together. I use the sample problems, and then I create a couple of extra sample problems that I put up, and then I turn my students loose. And I have heard that people on the train, when they're riding home on the train, have gotten involved with them talking about what they're doing. And so I think that the conversations that they're having around these questions are telling me that they are understanding what counting and accounting for matter in gases, and how gases have to be identified by their volumes. I think it gets through to them. Plus, I think the questions in this developing skills are really top-notch. The vocabulary is very strong, and the questions are well written. I like it. And in C8, this is a lab that I really hope you will try. Practice it yourself first. When you start to read the directions, work through it. You're going to use syringes, and you're going to use a little vial cap. And you're going to use the syringe as a chamber to generate carbon dioxide. And then you're going to do tests on the carbon dioxide gas. And the students will, you're not going to do it, you're going to do it when you practice, but then the students are going to do this. This is usually a 2-day lab because it takes us 1 day to practice how to generate the gas. And once the kids get it, they go forward gangbusters. In my school, we have only girls, so, but nonetheless, this is something that they are very successful for if I give them the time to figure out how to do it. And not only that, they're developing really top-notch lab skills, following directions. You know, that's, I don't know about your students, but my students really have to be sort of coerced to do that. They want to skip steps, but you can't do that with these labs. So they're in this lab, they're going to generate some carbon dioxide gas, and then in various part 2 of the lab, they're going to analyze the carbon dioxide with several different little experiments on the carbon dioxide. And I find that my students will lose all their gas, or something they'll have a mishap of some sort, and they'll go back and do it again without me prompting them to. So by this time in the year, I'm really impressed with the lab skills and direction that I have, have browbeat into them. This lab then follows up with interpreting evidence, making claims, and really strong reflecting on the investigation. All these steps with new titles. The new titles really changed the mindset of my students. They had a hard time concluding, but they can reflect very well. And I think the questions, especially in this lab, provide the students with some wonderful thought exercises. Concept check follows this. Again, what have we learned? What did Avogadro's law help us to interpret in chemical equations? And reactions, what 2 requirements for the reaction of gas molecules are identified by collision theory. So it's review, what did you learn, what do you know now, and then where are we going? And this section is, the kids are interested in this because they hear about global warming and greenhouse gases, and they have opinions. But this is going to attack it strictly from a scientific point of view. Where do we need to start? Well, we're going to start with the electromagnetic spectrum. And the kids may have had some of this information in previous classes. Our kids have had it in physics first, but this is applying it now. Okay, you know about radiation and different kinds of radiation that come from the sun, especially since we're in solar maximus now. So they're hearing about these things, and now we're going to take this information and we're going to apply it to our atmosphere. Again, there are some nice graphs in the book for the students to read. They don't look typical. There's a really nice graph on page 223 that is actually a picture of the electromagnetic spectrum depicted in an unusual way, as you can see here. The kids they know, but they don't actually realize what this electromagnetic spectrum is. And I take a little bit of time to talk about it. They have some knowledge, but we're applying it now to how does this interact with the atmosphere. This will be a review from the waves. And then we go on to one of my favorites, chemquandaries. How accurate is this statement? All radiation is harmful and should be avoided. And this becomes a classroom conversation that at times has gotten away from me because the students have strong opinions and knowledge now to take this conversation to a higher level. And this is where they are absolutely amazed to find themselves speaking like scientists with using evidence and information that they have. So don't skip these chem quandaries. They're truly wonderful and an opportunity for the kids to use their imagination. And then we go on more with the electromagnetic spectrum and solar radiation, and I always, because we're all girls, I always weave in tanning to this. It's just part of the lesson. And Earth's energy blanket, again, lovely pictures in the textbook of the clouds, cycles are introduced, and we'll go into greenhouse gases and greenhouse effect and what that is, and the connection of the solar radiation, the greenhouse effect, greenhouse gases to climate. Following that, we have a developing skills that talks about human exposure to ultraviolet radiation, sort of a rethinking of what we've just read and studied about. And then we go on to the last thing before we leave this is making decisions, making claims and providing evidence. The students will be asked to get in. I have them get into their lab groups, and again, they're going to follow up with A, B, and what they have answered in those making claims, and come up with some questions and evidence for where they're going with their experiment. Now, this I make as a homework. Mostly I have kids talk about their making evidences, making decisions, but for this one I have them write the answers out before they come to class, because I find that the quality of the conversation becomes much better. They're going to pull in information that they have gotten from section A, B, and C in this particular making decisions. And we follow up by the section summary, and I do have them do these, but I space them out, and they get assigned as we go through the section. And that leads us into the very last section, section D, and I think my friend Bonnie is going to take over, and she could add anything that I skipped over for section C. Please do, Bonnie. Hello? I don't hear Bonnie.
Bonnie, are you there?
Yeah.
Okay.
Okay.
Can you hear me now?
It's your turn.
Okay, I don't know what happened because I was talking and it wasn't.
Oh.
Great.
Oh, wow. Yeah, we didn't hear you.
Okay, well, I'll start again. Section D, we're talking about human impact on air quality, and the big ideas in terms of the theme of the unit are looking at experimental evidence and experimental results. So we're going to look at different types of pollutants. We're going to look at how we can reduce air pollution. Here is where we're going to start talking about acids and pH, and we'll look at acid precipitation, and then again we'll look at experimental results. So let's take a look at the concept check. And again, we're going to review air, and then what causes acid rain is the link to bring us to air pollution. So D1 starts to talk about the types of air pollutants. And so we spend some time learning about particulates, secondary and primary air pollutants, And there's some nice pictures in the book. There's talking about what the EPA does and how they're managing it. The ideas of where we can find the pollutants. And then part of D1 is also looking at the difference between the fact that there's natural air contamination, so air is not pure by any means, and it can't be pure because it's a mixture anyway, versus air pollutants that human activities contribute to. And so it talks about the idea that air quality is a problem when humans create too many air pollutants. And there's a pretty cool lab where they can make their own little ozone detector and then hang it outside for a little while. And then they make their own little particulate collector and they hang that one outside. And you get all sorts of really good things. The particulates are great if you have a dissecting scope. You take a dissecting scope and look at it, and you can see dirt and hairs and sometimes little bugs. And we did this in the winter one time. We saw a lot of salt. The detecting ozone, you can see there really is a difference depending on where you put it. We've put it near the cars, near the building in different positions, and they're fairly simple to make, but they're really instructive and they're pretty interesting as the students collect the data. They have a really good time with that. And then we're talking about different types of air pollutants. And as we talk about different types of air pollutants, first we look at how we sample them. And so this is about how do we collect data. And then, turn the page, we can take a look at where they sample them, and you can see where there are different sites. And I'm smack in the middle of Ohio, where there's a site. And it's interesting for students if they can try to figure out if there's a site near where they live. And so again, we're focusing on how do we collect data, where do we collect data. Sometimes we can even do it in aircraft. And as part of this data collection, this brings us back to accuracy versus precision. And this is a picture that I think a lot of students have seen before. I know we have almost the exact same picture in our 9th grade textbook. But they treat accuracy and precision, I found my students often treat them as synonyms. And so it's a really good time to talk about whether or not we're getting accurate information, whether or not we're getting precise information. Because if students are going to design their own investigation, they should know how do they know how accurate their data is and how will they make sure that it's precise. Now, this is tough for students because, as Linda was talking about before, they can make a graph, but looking at charts is a little more difficult. And our students have found, all the big tests, the ACT, the SAT, a lot of the state tests, all involve looking at charts and drawing conclusions from charts. So, as part of the whole focus on how do we do science, there's a nice section on what kind of conclusions can we draw from looking at the data in a chart form. And then there's another concept check. So we look at some air pollutants, why are some more concerned than others, and then we start to take a look at weather and climate, and that leads us into the next section, which is kind of fun. So it takes a look at photochemical smog, and it takes a look at the difference, an inversion layer, and how you end up with smog. And I actually found some pretty good web clips of Denora and talking about what happened there and their smog. But then there's a different way for students to look at graphs. So we can see temperature and altitude, and we can see what's happening with the cool air and then the inversion layer trapping this air. And we talk about synergistic, and we talk about the interactions of the air. And again, we're looking at developing skills. This one is really, can you look at these charts and can you look at this bit of information and answer questions? And I assign this usually as a homework, and then we discuss it the next day. And my students are pretty successful with this. This is really just looking at data and making interpretations. Then we have a chem quandary, and those are always a good discussion question. Why is it more difficult to control pollution from automobiles and moving vehicles than from power plants and industries? And the students come up with a lot of different ideas. There are some better answers than others, but there's not exactly the correct answer. And then the pollution ties us into acid, base, and the pH scale, because we talk about acid rain and acid precipitation. So we review the idea that normal pH is 7, above pH 7 is a base, below pH 7 is an acid. And so we're going to do a little bit with this now, and then we're going to come back to it again in Unit 4 in a lot more detail. And so here we're writing equations. So what happens when a gas molecule reacts with water to form an acid in the atmosphere? And so this information has them, again, looking at equations, looking at balanced equations, law of conservation of matter, as well as being an introduction for the lab that's going to come next. And this is a cool lab. There's some metal, there's a pH indicator, there's usually a marble chip or some calcium carbonate, and then there's apple or plant material. And by mixing a little bit of hydrochloric acid with the sodium sulfite right in the center, that produces the SO2, which then will dissolve in the water that is near each of these, and you can actually see the effects of the acid rain on the little bit of metal, the little bit of carbonate, the little bit of plant material, and the little bit of indicator. And it's small scale. If you've seen the older book, the older one was, you had to be careful because you could breathe in all the SO2. But this one is really nice. It's in a Petri dish. It's very well contained, and it's pretty easy for students, and they see pretty good results. And then we start taking a look at what happens as a result of the acid rain. And so that's what D10 is looking at. So again, we have a graph, and we can look at the pH of precipitation throughout the country, and we'll take a look at why, even though a lot of the coal-fired plants are right around here, kind of near where I live, it's a problem in the Northeast. And so we can talk about what kind of factors cause the acid rain to be moving. And there's some nice pictures showing some of the destruction and the damage. And I've actually gone to a cemetery, and I can find some old gravestones that are marble and are granite. You can actually take some pictures so that it's local to them too as well. And then this chem quandary is right going with that graph we just took a look at. Why does Maine have a low pH in their rain even though they don't have coal-fired power plants? And we just talked about that. And here, now they're coming back to their air quality issue or claim. And so here they're going to be making a poster that describes the investigation and writing a letter to the members of their local or national community. And again, so we can review everything. What is air pollution? How is it measured? We can take a look at what we need to, the techniques in terms of accuracy and precision, what photochemical smog can do, acids, bases, and neutral, acid rain and the natural pH of rain, and air pollution can be affected by everyday activities. And then again, there's always that big question that allows them to do the writing piece, the essay, that's part of the summary questions. And then here is our PIAT. And Linda, do you want to just wrap up with that PIAT?
Oh, you can.
Okay.
You're on a roll.
Really what they're doing is they're taking all the bits of their section A, B, C, and D and now putting it all together with the poster and the letter. So the way the unit is structured, they don't have to do a lot of new information gathering for their PIAT. It's really putting it together. They've gathered all the information. They've done all the pieces. Now it's just creating the final project to answer their theoretical investigation. And what we do is we put it together as almost a science walk where different students have their posters set up around the room and they have some questions, guiding questions, and they go around and they look at other posters to see what they can learn from the other students' information. And I think that's about it. Michael?
Yes. Thank you again, Linda and Bonnie. And thank you for participating. Linda and Bonnie will be happy to take any of your questions. If you want to write any questions and put them in the question box, I will copy them and post them, and Linda and Bonnie will be happy to answer that. For the attendees, I will be happy to, within the next week, I'll be sending you documentation from the American Chemical Society to participate in this webinar. And these webinars will be recorded, as they have been recorded, and they will be posted on our website so that if you want to watch them at any time or suggest that any of your colleagues watch them, they will be available for them as well. So the floor is open if anybody has any questions. So there, Bonnie and Linda, there's a question about how long does it typically take you to complete this unit?
I'm sort of doing a hybrid, so Linda, you're probably better at answering this question.
Well, probably together we could give you an answer. My classes are very short. I have 40-minute classes every day, and I get a double period once a week. I spend about a quarter on this. There's a lot of important chemistry in here. I think probably a little more time on Section A and Section B because I hit the gas laws pretty hard. They're going to need that. Our students take biology junior year, and our biology teacher finds that she can go into a lot more detail because the kids, she doesn't have to teach them the chemistry. They're already at a higher level, and we all know that biology is all chemistry now. So I do spend about a quarter. Bonnie?
I'm about a quarter as well. We have it for some strange reason, our first semester is shorter than our second semester. So, but it turns, so there's some overlap over winter break. I usually get to D, like in January. But it is about a quarter.
Okay. So Kevin, if you want to get a sample copy, I would suggest contacting your W.H. Freeman rep, and if I remember correctly, you're in Arizona, and that is Chad Listener. His email is clistner@bfwpub.com. And just tell him that you participated in the webinar and you'd like to get a copy of ChemCom 6th edition, and he will gladly send it to you. Okay, do we have any other questions? Well, I want to thank our presenters again. Thank you so much, Linda and Bonnie, for joining us tonight. And I want to thank all of you for joining us tonight, and have a wonderful evening. If you have any questions at any time, please do not hesitate to contact me. You can reach me at ChemCom, ChemCom, @acs.org. Have a great night, everybody.
Good night.
Night.